C# and AI Masterclass by Edgar Milvis Volume 8, Chapter 6. Now, let's explore Chapter 6, Native Functions, calling C# code from LLMs, moving on to theoretical foundations. The fundamental challenge in building robust AI agents is not the generation of text, but the reliable execution of deterministic logic. While large language models, LLMs, excel at pattern recognition and natural language synthesis, they are inherently probabilistic and stateless. They cannot natively perform complex calculations, maintain transactional consistency, or interact with external systems with guaranteed precision. This is where the concept of native functions becomes the linchpin of AI engineering. By bridging the gap between the probabilistic world of the LLM and the deterministic world of compiled C# code, we create a hybrid system that leverages the strengths of both. Now, let's explore the probabilistic versus deterministic divide. To understand the necessity of native functions, we must first appreciate the architectural schism between an LLM and a traditional software system. An LLM operates within a high-dimensional vector space, predicting the next token based on statistical likelihood. It does not know how to calculate the square root of a number, it merely predicts the characters that would likely follow the prompt, what is the square root of 144, based on patterns in its training data. While it might correctly predict 12, it has no internal calculator. Conversely, a C# application is a sequence of deterministic instructions executed by the Common Language Runtime, CLR. When a C# method is invoked, the input maps to a specific output with 100% repeatability, assuming no external state mutation. The challenge, therefore, is to allow the LLM to request the execution of a deterministic function while remaining in its conversational flow. We need a mechanism that allows the LLM to say, I need to perform a calculation, and for the system to reply, here is the result, allowing the LLM to continue its reasoning. This is analogous to a general contractor, GC, and a specialized subcontractor. The GC, the LLM, understands the overall blueprint, the user's intent, and can communicate with the client. However, the GC cannot pour concrete or wire electrical circuits. Instead, the GC issues a work order, a function call, to the subcontractor, the native C# function. The subcontractor performs the specialized work with precision and returns a completion report. The GC then integrates this report into the broader project plan. Without this delegation, the GC would be forced to guess how to pour concrete, likely resulting in a structural failure. Turning our attention to the mechanics of bridging the gap. In the context of Microsoft's Semantic Kernel, the bridge between natural language and native code is built using plugins and kernel functions. A plugin is a logical grouping of capabilities, while a native function is the atomic unit of execution. The core mechanism relies on reflection and attributes. When we define a C# method and annotate it with the kernel function attribute, we are signaling to the semantic kernel runtime that this method is callable by an LLM. This is not merely a marker, it instructs the kernel to build an internal manifest of the function's capabilities, including its name, description, and parameters. The semantic kernel utilizes this metadata to perform automatic parameter binding. When an LLM generates a function call, via standard JSON schema formats, the kernel parses the arguments provided by the model. It then maps these arguments to the C# method's parameters. This mapping is sophisticated, it handles type conversion, JSON serialization, and even complex object hydration. Consider the requirement for complex input-output types. The LLM does not natively understand C# classes or structs. It operates on text tokens. Therefore, the kernel acts as a translator. It serializes complex C# objects into JSON for the LLM to reason about, and upon receiving a function call, it deserializes the JSON back into strongly typed C# objects. This allows us to pass rich domain models, such as customer order or financial report, between the LLM and our native code. Now, let's explore the role of strong typing in modern C#. In earlier iterations of AI integration, developers often resorted to string parsing or loosely typed dictionaries to handle function arguments. This approach is fragile and error-prone. Modern C# features allow us to define these native functions with strong typing, leveraging the compiler's safety checks. For instance, using record types for parameter objects ensures immutability and value equality, which is crucial when dealing with stateless function invocations. The kernel's ability to bind JSON data to these records relies on the system text JSON serializer, which is highly optimized for performance. Furthermore, the use of async enumerable T allows native functions to stream results back to the LLM. This is critical for long-running operations, e.g., querying a massive database, where waiting for the entire result set would cause timeouts. The LLM can receive chunks of data and process them incrementally, mimicking a real-time conversation. Now, let's explore architectural implications, the orchestration layer. The introduction of native functions shifts the architecture of the AI application from a simple, prompt-response loop to a sophisticated orchestration layer. In Book 7, we discussed the concept of the kernel as the central nervous system. To recap, the kernel is the orchestrator that manages memory, plugins, and the underlying AI services. When we expose native functions to the LLM, we are essentially equipping the kernel with a toolkit. Intent recognition: the LLM analyzes the user's input, e.g., what is the total value of pending orders for customer ID 451. 2. Function selection: the LLM determines that the getPendingOrders function is required to answer the query. 3. Argument generation: the LLM generates the arguments, e.g., customer ID 451. 4. Kernel invocation: the semantic kernel intercepts this function call. It looks up the corresponding native C# method. 5. Execution: the kernel invokes the C# method, passing the deserialized arguments. 6. Result return: the native method executes, e.g., querying a SQL database, returns a list order. 7. Context augmentation: the kernel serializes the result and injects it back into the chat history as a tool message. 8. Final synthesis: the LLM sees the tool message, reasons over the data, and generates the final natural language response. This architecture allows the LLM to act as a reasoning engine rather than a database. It offloads the heavy lifting of data retrieval and calculation to the native code, ensuring accuracy and performance. Moving on to the switchboard analogy. To visualize this relationship, imagine a telephone switchboard operator, the semantic kernel. The caller, the LLM, wants to connect to a specific department, a capability. The caller doesn't know the direct extension numbers, they just ask the operator to connect me to billing. The operator, kernel, consults a directory, the plugin manifest. This directory maps the request, billing, to a specific physical line, the native function. The operator plugs the cable into the jack, parameter binding, and establishes the connection, execution. The conversation that follows, data flow, is routed through the switchboard. If the switchboard operator didn't have this directory, no, kernel function, attributes, the caller would be shouting into the void. If the mapping was manual and error-prone, loose typing, the caller might be connected to the wrong department. The native function mechanism provides the standardized directory and the reliable cabling. Moving on to visualizing the flow. The following diagram illustrates the flow of control and data when a native function is invoked by an LLM via the semantic kernel. This diagram illustrates the semantic kernel invoking a native function, where the standardized directory acts as a map to locate the function and the reliable cabling ensures the secure and efficient transmission of data and control flow between the LLM and the native code. Now, let's explore edge cases and error handling. Type mismatches: if the LLM generates an argument of the wrong type, e.g., passing a string, 1, to an int parameter, the kernel's binding mechanism will throw a kernel exception. It is the responsibility of the function author to handle validation or for the kernel to provide fallback logic. 2. Complex object hydration: when a native function requires a complex object, e.g., search parameters containing nested filters, the LLM must generate a JSON object that matches the schema exactly. The kernel uses the JSON serializer options to map snake_case or camel case JSON properties to Pascal case C# properties, but strict adherence to the schema is required. 3. Async operations: native functions often involve I/O. The kernel supports async natively, but the LLM's context window is finite. If a native function takes too long to execute, the conversation state may expire. Strategies like deferred execution or polling via native functions are required for long-running tasks. Moving on to why this matters for AI engineering. The ability to call native C# code is not just a convenience, it is a requirement for production-grade AI systems. Without it, we are limited to the LLM's training data, which is static and prone to hallucination. Access real-time data, query live databases or APIs. Perform calculations, execute math, statistics, or logic that requires precision. Manipulate state, create files, send emails, or update records. Enforce security, run sensitive logic within the safety of the backend application rather than exposing it to the prompt. In the subsequent sections of this chapter, we will move from theory to practice. We will define the kernel function, attributes, explore the serialization strategies for complex types, and demonstrate how to configure the kernel to expose these functions to an LLM for function calling. We will see that the magic of AI is not in the model itself, but in the engineering of the bridge that connects it to the real world. Now, let's talk about basic code example. At the beginning, we bring in essential namespaces. Microsoft.Semantic Kernel is the core library for building AI applications with Semantic Kernel. Microsoft.Semantic Kernel connectors.OpenAI provides the necessary components to integrate with OpenAI models, which is a common choice for LLMs. The system.component model namespace is crucial for attributes like description, which we'll see later are vital for the LLM to understand our C# functions. Finally, system, text, JSON and system, text, JSON, serialization are included for efficient JSON serialization and deserialization, a fundamental aspect of how Semantic Kernel passes data between the LLM and your C# code. This choice reflects modern.NET's preference for system, text, JSON over older alternatives like JSON.NET for performance and native integration. Here, we define our first data structure, weather request. This class serves as the blueprint for the input parameters our native C# function will expect. Notice the JSON property name attribute on city and unit. This is a system, text, JSON attribute that dictates how these properties will be named when serialized to or deserialized from JSON. This is critical because LLMs often generate JSON payloads with specific key names, and this attribute ensures a seamless mapping to our C# object. The description attribute is equally important. It provides human-readable context about each parameter, which the semantic kernel uses to generate a schema that the LLM can understand, allowing it to correctly formulate function calls. Without these descriptions, the LLM wouldn't know what city or unit means in the context of our function. Next, we define the weather response class. This structure represents the expected output when our native C# function successfully executes. Just like with weather request, we use JSON property name attributes to ensure that the properties of this C# object map correctly to JSON keys. This consistency is vital for the semantic kernel to properly serialize the C# function's return value into a format that the LLM can consume and interpret. For instance, after our C# function fetches weather data, it will populate an instance of weather response, which the semantic kernel will then convert into a JSON string for the LLM to process and use in its natural language response. This clear contract between input and output type simplifies the integration between the LLM's reasoning and your application's logic. This section introduces the weather plugin class, which is where we encapsulate the actual C# business logic that the LLM will be able to invoke. The kernel function attribute is a cornerstone of semantic kernel. It explicitly marks the getWeatherAsync method as a function discoverable and invocable by the kernel. Without this attribute, the kernel would simply ignore the method. The description attribute on the method itself is paramount. It provides a clear, concise explanation of what the function does, which the semantic kernel uses to generate a function description for the LLM. This description is how the LLM understands the purpose of the function and decides when to call it. Furthermore, notice the description attributes on the method parameters, city and unit. These provide crucial context to the LLM about what kind of data each parameter expects, guiding the LLM in constructing the correct arguments for the function call. The unit parameter also has a default value, Celsius, demonstrating how you can provide fallback behavior directly within your C# function definition. Inside the getWeatherAsync method, we find the core logic for retrieving weather information. Observe the await task, delay, 100, at line 58. This line simulates network latency, which is a common characteristic of real-world API calls to external weather services or databases. In a production environment, this would be replaced with an actual HTTP client call to a third-party weather API. The subsequent lines, from 60 to 68, implement mock logic to generate a random temperature and condition. We're using random to produce a varied output for demonstration purposes. This deterministic C# code execution is a key advantage of native functions. The LLM delegates a specific task to reliable, predefined code, ensuring accuracy and control over the actual data retrieval and processing. This separation of concerns allows the LLM to focus on natural language understanding and generation, while your C# code handles the precise, deterministic tasks. Lines 70 through 82 continue the logic within getWeatherAsync, focusing on temperature conversion and result construction. If the unit parameter, provided by the LLM, is to Fahrenheit, the code performs a simple conversion from Celsius to Fahrenheit. This demonstrates how the C# function can dynamically adjust its behavior based on the LLM's input. Finally, an instance of weather response is created and returned. Notice math, round, temp, 1, at line 79, which ensures the temperature is formatted to 1 decimal place, demonstrating attention to detail in data presentation. This weather response object is what the semantic kernel will then serialize into JSON and pass back to the LLM. This structured return type is essential for the LLM to consistently understand the output of your tool, enabling it to formulate a coherent natural language response to the user. Moving into the program class's main method, we begin the setup phase for our semantic kernel application. The first crucial step is initializing the kernel itself. We use kernel.createBuilder to start the configuration process. Notice add OpenAI chat completion at line 95. This method integrates an OpenAI chat completion model into our kernel. For this example, model ID, GPT-4o mini, is specified, a cost-effective and capable model. Crucially, API key, fake API key for demo, is a placeholder. In a real application, you would never hard-code an API key like this. Instead, you would retrieve it from secure environment variables, Azure Key Vault, or another secure secret management system. This setup establishes the communication bridge between our C# application and the underlying large language model, enabling the AI to process requests and interact with our defined functions. At line 100, we perform a vital step, importing our native C# plugin into the kernel. Kernel.import plugin from object, new weather plugin, weather, tells the semantic kernel to inspect the weather plugin class. The kernel then scans this class for any methods adorned with the kernel function attribute, like our getWeatherAsync method. It automatically registers these methods as callable functions, making them available for the LLM to discover and invoke. The string weather provides a namespace for our plugin, which helps organize functions, especially in applications with many plugins. This architectural decision allows for modularity, meaning you can easily add or remove functionalities by simply importing or not importing specific plugin classes. Next, we prepare the kernel arguments at lines 105 to 109. This dictionary-like structure holds the parameters we intend to pass to our getWeatherAsync function. The keys, city, unit, must match the parameter names expected by the C# method, as the semantic kernel handles the serialization of these arguments into a format the C# method can consume. This explicit argument preparation is essential when you want to directly invoke a function, bypassing the LLM's decision-making process. At line 116, we demonstrate a direct invocation of our native C# function using await kernel.invokeAsync plugin, getWeatherAsync arguments. This is a powerful feature for several reasons. Firstly, it allows for direct testing and debugging of your native functions without needing to go through the entire LLM interaction loop. Secondly, it's useful for scenarios where you, as the developer, already know exactly which function needs to be called and with what arguments, perhaps based on a user interface action or a specific application state. In such cases, involving the LLM in the decision-making process would be an unnecessary overhead. The plugin, getWeatherAsync, syntax retrieves the registered getWeatherAsync function from our weather plugin. The arguments object, prepared earlier, is then passed to it. Finally, line 120 prints the result. The semantic kernel automatically handles the deserialization of the weather response object returned by getWeatherAsync back into a usable format, which can then be displayed or further processed by your application. This direct invocation highlights the flexibility of semantic kernel, allowing both LLM-driven and developer-driven function execution. This commented section from lines 123 to 131 is incredibly important as it outlines the full, agentic flow, the typical interaction pattern when an LLM is actively involved in orchestrating function calls. It's a conceptual roadmap that clarifies why we build native functions. Notice that the user's natural language request, step 1, kicks off the entire process. The LLM then acts as an intelligent agent, step 2, analyzing the intent and determining the need for a specific tool, like our getWeatherAsync function. Step 3 is where the LLM constructs the necessary JSON arguments, leveraging the description attributes we added to our C# methods and parameters. Steps 4, 5, and 6 describe the semantic kernel's crucial role, bridging the gap between the LLM's JSON output and our C# code, executing the C# function, and then converting its C# object return value back into JSON for the LLM. Finally, in step 7, the LLM takes the structured result and synthesizes a natural language response for the user. This entire sequence illustrates the power of semantic kernel in enabling LLMs to interact with external systems and perform real-world actions, moving beyond mere text generation to intelligent automation. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. Thank you for your attention. This lesson is excerpted from Volume 8, Chapter 6 of the C# and AI Masterclass ebook series and from the volume, The Core of AI Engineering, Microsoft Semantic Kernel and Agentic Patterns. You can find all the details here, https://github.com/edgarmilvus/C# programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.